Okay, hi everyone. Welcome back to HoloTube after the Easter break, and we're very happy to have. Okay, this is not the first one after the Easter break. Sorry, the second one. But we're very happy to have Andrei Parnachev from Trinity College in Dublin, who will tell us about heavy and thermal states in CFT and holography. Please, Andrei.
Thank you. Well, thank you for inviting me. It's a pleasure to give a talk here. So I will talk about heavy and thermal states in conformal field theories in higher than 2 dimensions and the relations to holography. And yeah, please, at any time, you are more than welcome to interrupt me and ask me any questions. So I'll try to keep it informal. So what I'm going to talk about today is based on work in collaboration with Robin Carlson, Manuela Kulaksizi, Gimsem G, Carlos Sen, and Petr Tadic. So let me start by reminding you that in these space-time dimensions, there are conformal field theories, which form an important set of quantum field theories. They're invariant under scaling, among other things. And in addition to scaling, they have, of course, the usual Poincare symmetry, and also something called special conformal transformations. And an important set of operators are so-called primary operators, which are annihilated by these special conformal transformations. So these primaries usually have definite scaling transformation when you just take each space-time coordinate and multiply it by a number. And so this scaling is generated by the dilatation operator D. And the eigenvalue of the dilatation operator is called conformal dimension delta K. So all other operators in CFTs are descendants of these primaries, which you can get by basically acting by momenta. And so these are essentially derivatives acting on the primaries. So because of the conformal symmetry, simple correlation functions like 2- and 3-point functions, primaries, are completely fixed by word identities. So in particular, if we consider scalar operators, then the 2-point function is completely fixed, and it's only non-zero when the 2 operators have the same scaling dimension, and the scaling is again completely fixed. And the 3-point function is also fixed. So if you have 3 operators inserted at 3 different points, then the space-time behavior of this 3-point function is completely fixed by this denominator here. And lambdas, which appear in the numerator, are important objects called the OPE coefficients, where OPE stands for operator product expansion. And operator product expansion is simply a statement that if you take 2 operators, one at x and the other at 0, then you can expand this product in the basis of operators sitting at 0, with the coefficients appearing in this expansion being precisely the OPE coefficients. And you can see that if you dot this formula with OK, take the expectation value, you get precisely this. Using this, you get precisely this. So 2- and 3-point functions are fixed, but things become more interesting when you consider 4-point functions. Let's consider, for simplicity, the 4-point function of pairwise identical operators, O1 and O2. And you can always use conformal symmetry to bring the, and by the way, what I'm talking, I mentioned this already, let me just emphasize it one more time, that essentially everything I'm going to talk about today is going to happen in a number of dimensions greater than 2. In 2 dimensions, things in a way are much simpler, and I will say a few words about 2-dimensional case, but mostly I'll be talking about d greater than 2, and in certain situations I'll specify to d equals 4. Anyway, so the 4-point function is more interesting, you can always use conformal symmetry to bring three operators to infinity, 1 and 0, and everything will then depend on two variables, so-called z and z bar, which are also called conformal ratios, cross ratios. And these are basically the positions of the insertion of this operator. And they're related to the original positions of your operators in space-time. So this 4-point function now has non-trivial dependence, and it admits a conformal block decomposition where b, k, which is a function of z and z bar, are known functions, and they contain contributions from primary OK and all of its descendants. And the coefficients that appear here are the OP coefficients when you fuse 1 and 1 operator with OK and 2 and 2 operator with OK. So these are the OP coefficients. Now, another important object in CFTs is something called the central charge, and it appears in the 2-point function of the stress tensors. So the 2-point function of the stress tensors is completely fixed up to a number. So the x dependence is fixed by this object, where I is this formula, and Ct, this number that appears in front, is precisely the central charge. And in the following, I will only talk about CFTs, where the central charge is very, very large, much greater than 1. And for reasons which all of you know, I'll often say that Ct is the same as n squared. So that's, of course, when we think of n equals all super n Mills or some other examples, well, n equals all super n Mills is probably what everyone thinks of at the moment. So n is just n in SUN. So the central charge in n equals all super n Mills is precisely scales like n squared. But what I'm going to say mostly is going to be applicable for any large CFTs. And in such CFTs, major players are so-called double trace operators, which are basically two single trace operators, two primaries, with a bunch of derivatives and boxes inserted. So we have to, and the number of derivatives is counted by L, number of boxes is counted by N, and the difference between boxes and derivatives is that N does not increase spin, but increases conformal dimension, while L increases spin. So by this, I mean a bunch of uncontracted derivatives. So L is the spin of this operator. And for unit normalized operators, the OP coefficients of O1 with double trace operator made out of the same operator scales like 1, and the OP coefficient of O1 with the double trace operator made with a different operator is suppressed. And all of this you can see very clearly in holographic CFTs. For example, if you are interested in the leading 1 over n squared term in the 4-point function, then one contribution that you can get is something that you get from a very simple Witten diagram, where you have two scalar propagators here and here, and they're connected by a graviton in the middle. So you can ask a question, how does this Witten diagram decompose into conformal blocks? And precisely this question was answered by these guys. So in particular, one thing that you might immediately guess is that the graviton exchange naturally should correspond to the stress tensor exchange. So there has to be a stress tensor in this conformal block decomposition, and the OP coefficient of the stress tensor with any operator is completely fixed by a word identity. So in particular, you can say that immediately that the stress tensor contributes delta 1 over square root of CT times delta 2 over square root of CT, and that in this case like 1 over n squared. But it turns out that if you are going through the decomposition of the Newton diagram, in addition to the stress tensor, you will find that there are other operators that contribute in the conformal block decomposition. These other operators, so naively you think that the stress tensor would be the only thing, but it's not the case. So there are other operators. These are the double trace operators made out of O1 and O2. So where O1s are here and O2s are here. So so here, if you do the conformal block decomposition, there's a stress tensor, but then there's also double traces due to O1, double traces due to O2. And the OP coefficients of these guys are completely known. You can read it off from this Witten diagram. And in particular, if we look at here, I think this formula is a bit misleading, but the product, so there should be O2, O2, O1, O1 here. So if you're interested in the contribution of O1, O1 double trace operator, and then this whole contribution scales like 1 times 1 over CT, which also scales like 1 over n squared. But in fact, the numbers also know. So we know everything about this diagram. Now, natural question you may ask is what happens if we start adding graviton loops? And of course, graviton loops are further suppressed by the powers of G Newton, or equivalently by the powers of 1 over n squared. And so you can, so here's an example of one loop diagram. Here's an example of another loop diagram. And that further suppressed. But we can simplify the situation a little bit by making one pair of the scalar operators to be heavy. And when I say we're making them heavy, what I mean is we take their conformal dimension and make it scale with CT. So conformal dimension of this guy scales with CT, or equivalently scales like n squared. So in this case, these interaction vertices, which come with a factor of n squared, balance out the loop factor, and these diagrams are no longer suppressed. So all loop diagrams of this type will survive in the large unlimit. Diagrams of this type will all disappear. And this is interesting for a variety of reasons. In particular, it will give rise to various classical effects. So you may think, well, by now people familiar with this, but naively one may think, well, there are loop diagrams, must be quantum gravity and so on. But it turns out that these loop diagrams, if you sum over all of them, they will be responsible for classical effects. So now at this stage, natural question is, what is the dual object to a particle whose mass scales like CT, or equivalently like n squared? And the answer is, it's an ADS-Schwarzschild black hole. Let me remind you what an ADS-Schwarzschild background is. So the metric is given by this formula. So it's asymptotically anti-de Sitter. In particular, for large radii, for large R, this term disappears, and you just end up with anti-de Sitter metric. So that's the meaning. It's asymptotical anti-de Sitter. But for finite R, there is a horizon somewhere. So it's a black hole. And there is one parameter mu here. R is a radius of ADS. And there is a parameter mu here, which is related to the mass of the black hole in this way. It's proportional to G Newton, proportional to the mass of the black hole, and inversely proportional to R to D minus 2. Now, let me remind you that we have a map between conformal dimension and the mass. So remember, we're trying to understand what's going to be the conformal dimension of this object. And the map between conformal dimension and the mass is just this. So we substitute it in here, substitute mass equals delta H or R in here, and use the fact that R to power D minus 1 over G Newton scales like a central charge. This is a standard ADS dictionary. So mu, which is constant for black hole, is just a ratio of delta heavy over CT. So therefore, if we take delta heavy to be a water CT, and then further take CT to infinity, keeping this ratio fixed, then the the background which corresponds to this heavy particle is precisely a black hole.
Sorry, Andrei, there is a question by Alex in the chat that he doesn't have a mic, and he asks how such a map works given that a black hole has an entropy.
Yes, so good. So that of course is another way to ask this question is how do you know that it's a black hole and not some kind of isolated state? So how do you know it's not some heavy state? That would be, I guess, a different way to ask this question. And I was going to mention, I'm going to, this is a good question. Let me move to the next slide where I'm going to comment on this. So this is a comment on this. But before I get into this, let me just say that we are going to, so what we're going to do is we are going to study the heavy light correlators, which are these 4-point functions where 2 operators are heavy and 2 operators are light, and they correspond to probing heavy states with light operators. And by what I just said, by holography, they are mapped to 2-point functions of light operators in the black hole background. Now, black hole is, of course, a thermal state with entropy. So, as I said, somewhere I assumed that heavy state becomes a thermal state, or equivalently thermalization happens. So let me put it this way. Let me make it like, well, in holography, where we have strong interaction, it's a natural assumption. So let me make this assumption, and then they will see that this assumption is consistent with the physics. Okay. Now, let me also mention that these diagrams with loops, they basically involve multiple gravitons. So there are lots of gravitons which end on this heavy state. And then you can ask a question, what is the meaning? Just like we ask a question, what's the meaning of a single graviton exchange from a CFT point of view? We can ask a question, what's the meaning of this multiple graviton exchange from a CFT point of view? And natural answer, which turns out to be correct, is that they are mapped to multi-stress tensor exchange. So now, in addition to the stress tensor, we will need to consider conformal blocks due to multi-stress tensors. So these multi-stress tensors are simply products of stress tensors. And these are going to be very important players in this game. And then there are other operators which involve, which are analogs of multi-trace operators, which appeared in the single graviton exchange case. But I'm mostly not going to talk about those.
Hi, Andrei. Can I ask a question related to what Alex said?
Yeah.
So would it, if you treat the heavy operator as a thermal state, would that mean that, let's say you compute heavy energy and heavy operator 3-point function, would that be non-zero?
Sorry, can you say it again? So,
so let's say I want to compute, let's say I want to, if it's like a thermal, if inserting heavy operator is like a thermal state, then wouldn't that mean that if I compute, let's say thermal 1-point functions?
Oh yeah,
or like heavy energy heavy, would that be non-zero?
Exactly. Yeah, very good question. So that's what like part of my talk is going to be about precisely. I will discuss how well stress tensor is kind of boring, but we will see how. So what you're saying is precisely the statement of thermalization. The 1-point function of an operator in a heavy state is the same as a 1-point function operator of this operator in the thermal state, and I'm going to discuss it later.
Okay.
This turns out to be the case. So, but I will discuss in detail.
Okay, thank you.
Thank you. Any other questions? Okay, so as I said, excuse me, as I said, we will mostly be interested in the contribution of the multi-stress operators, which we also call the stress tensor sector of the correlator. And let me just remind you that in 2 dimensions, the stress tensor sector of a heavy light correlator has a name. It's called the Virasoro vacuum block. And there it's explicitly known. It has been explicitly computed due to the existence of the Virasoro symmetry. It's a very nice, it's a non-trivial, nice computation, and you have a very nice result. And there you see that that object thermalizes very quickly. So you can observe that the heavy light correlator is precisely the thermal 2-point function, because you know the thermal 2-point function in 2D, simply because you know the conformal map from a plane to a cylinder, to a thermal cylinder. So there, everything is nice. Here, things are more complicated because there is no Virasoro symmetry. That's what we are going to discuss. Now, one question that you may ask is, okay, so this multi-stress tensors are very interesting, but no, I just told you that there are other operators, let's say the double trace operators made out of external scalars. What about those? Like, I'm not going to talk about them. So what's their meaning? And the answer is, well, and there are other operators. If you go to weak coupling, there are all sorts of other operators which may contribute to your correlator. However, in strongly coupled theories, for example, in holographic theories, there are very few light operators. So you can decouple all these other light operators, yet the double trace operators will still remain. This, it turns out, you can also decouple. So there are a variety of questions that you can ask, which are only sensitive to the stress tensor sector, or equivalently to these operators. So one way to ask this question is to take the limit of large delta L. So it's not as large as n squared, but it's much larger than 1. In this case, the double trace operator has dimension 2 delta L, and it decouples simply because it's heavy. It's much heavier than the multi-stress tensors. So that's one simple limit. And this is the limit where in holography, the calculation is given, like if you compute a 2-point function, black hole background, it's basically just the length of geodesic. So it's something that you can easily compute and compare. In addition, there are some other observables, like a phase shift, which are also insensitive to double traces. And if that's not sufficient, let me give you another take on this. So consider probing heavy states with light operators, but very specific light operators. Consider probing heavy states with the stress tensors. So then, I called heavy light operators correlators which involve light scalars. So to distinguish the correlators with stress tensors instead of light scalars, I call the corresponding correlators heavy TT, HHTT correlators. And now the double trace operators are the same as the double stress operators. So in a way, there's no distinction. So the stress tensor sector is all there is to it. And of course, the TT correlator in the heavy state, or in the thermal state, since I promised that it thermalizes, is the thing that encodes hydrodynamics. So it's physically relevant. Okay. So these are the reasons why the stress tensor sector is very interesting. I think any questions? So this more or less concludes my introduction. Any questions about this? Okay, so the rest of my talk has 2 parts. The first part involves an additional limit, which turns out to be interesting, which is called a near lightcone limit. So there, what we do is we simply take light operators and take them close to each other's lightcone. And no, it's interesting for a variety of reasons, this limit, and I'll try to discuss it. So in particular, it turns out that you can compute the correlator by doing bootstrap. You don't even need holography. Turns out that you can assume a very specific form of the correlator, which is an educated guess coming from various observations. And once you fix this form, you can bootstrap it, and you see that it works because the number of equations that you get from bootstrap is much larger than the number of unknowns, and so you have an over-constrained system which is which still works, and you can get some nice formulas. And I will discuss the relation of these formulas to some entertaining combinatorics, like generalized Catalan numbers. And in the second part of my talk, I will talk about thermal physics. In particular, I'll talk about thermalization and mention a few things about some puzzles about heavy TT correlators. So that's the plan. So let's start by talking about kinematics. So we are considering a situation where we have two heavy operators, let's say on the Lorentzian cylinder, two heavy operators, which are inserted at plus and minus infinity, and two light operators, which are inserted somewhere in the cylinder. So this is d minus one dimensional cylinder, sorry, d minus one dimensional sphere, and vertically, time runs vertically. And the only thing that this correlator depends on, so one operator you can put at 0, 0. So the only thing that this operator, this is this guy. So the only thing that this correlator depends on is the separation in the time direction of the other operator, delta t, and separation in the angular direction of the sphere, delta phi. And you can show very easily that the cross ratios are related to delta t and delta phi by these formulas, z and z bar. So the stress tensor exchange, now let's discuss the conformal block decomposition of this correlator. The stress tensor exchange produces, remember that mu was delta heavy over Ct. So the stress tensor exchange produces order mu term, which is completely fixed by word identity. And the reason is, so the stress tensor OPE with heavy is proportional to delta heavy over square root of Ct, and with light is just 1 over square root of Ct. So it's delta heavy over Ct, which is precisely mu. So this is completely fixed. This is fixed by the word identity. There's nothing particularly exciting there. Things become much more interesting at order mu squared. Remember, mu squared is delta heavy over Ct. Mu is delta heavy over Ct. So single stress tensor contributes mu, double stress tensor contributes mu squared, and so on. But there are many double stress tensors. Double stress tensors are operators of this type. All of these operators are double stress tensors because there are two stress tensors, but now I can insert a bunch of derivatives in a variety of ways. So if I don't contract any indices, then these are leading twist double stress tensors. With the twist, which is spin minus conformal dimension, being 2 times d minus 2. If I start contracting indices, and I get subleading twist and more subleading twist and so on. And at each mu to the k, I have the same structure. So the structure is complicated, and this issue doesn't arise in 2 dimensions. So in 2 dimensions, there is no issue of twist. If you are talking about, let's say, holomorphic operators, twist 0. Now, to compute the whole stress tensor sector, we need to know OP coefficients of all of these guys. But things simplify in the lightcone limit, where z bar goes to 1. So by z bar goes to 1, I mean delta t over r minus delta phi go to 0. So these two guys go very close to a lightcone of each other. And in this case, first of all, it's a known fact that the lightcone OP is dominated by operators of the lowest twist. This is just a very easy exercise. So if we have, let's say, 2 scalar OPs, and somebody who has some bunch of spin L, so there are a bunch of indices here, then the only way you can contract these indices is by adding x's here. Then the guy that appears in the denominator is x squared tau over 2. This is just fixed by conformal dimension. So notice this tau, which is a twisted operator, this operator that appears here. And the lightcone limit is a limit where all x mu are finite, but x squared goes to 0, taking it close to lightcone. So now you see that the smallest twist dominates lightcone P. And this is reflected in the near lightcone behavior of the conformal block. So it's interesting. So these guys computed the OPE coefficients of operators, of light operators and double stress tensors, and observed that for leading twist operators, these coefficients are not affected by high order gravitational terms in the bulk. So there was some interesting universality. And one limit that we can take is we can take this double scaling limit where we take z bar to 1, which is a lightcone limit, and mu to infinity, so that this ratio is fixed. In this case, all high twist operators, all lowest twist operators contribute. So at each order in mu. So the reason why this limit is interesting is because it's the most direct analog of the two-dimensional case where we get the Virasoro vacuum block. And it turns out that that in this limit we can bootstrap the correlator and find a solution order by order in mu tilde. Remember, mu tilde measures the number of stress tensors. So the way it works, let me try to roughly give you an idea how it works. So order mu result, this is just a stress tensor, and it's completely fixed and it's given by this, where f is some hypergeometric function. The point is that it's completely fixed. We know it. It comes from the near lightcone behavior of the conformal block of the stress tensor. And then you make an educated ansatz that order mu squared result has some coefficients, and these coefficients multiply f3 squared, f2, f4, f1, f5, and so on. Notice that there are 2 f's in each term, and the sum of subscripts adds to 6. And then order mu cube, we claim, is again some coefficients. Now in each term there are 3 f's, and the sum of subscripts adds to 9, and so on. So this is the ansatz. So if you assume this, it turns out that you can determine all these coefficients by bootstrap. Yeah, I don't know if I should go through this, but okay, let me try to briefly go through this. So the stress tensor contribution you can write in this way. And the cross channel, so then when you say bootstrap, you need to analyze the correlator and the cross channel, where you fuse together heavy light and heavy light operator. And in these heavy light operators, the conformal data involves anomalous dimensions of heavy light operators. So these heavy light operators have spin L and twist n plus L. N is basically the number of boxes that you insert. And the anomalous dimension must have this form in order to reproduce this kind of formula. And the same form the OP coefficients also should assume the same form. So by matching this to this, you can determine all anomalous dimensions and all OP coefficients at order mu. But that completely fixes all terms that behave like log squared at order mu tilde squared. And because the ansatz, there's some question in the chat, I think, or
no, maybe you're just seeing the sign for the old question.
So because of the rigidity of the ansatz, you get a complete formula at order mu squared. And the complete formula at order mu squared turns out to be this. So it's not even that hard. And then you do the same exercise over the cube and so on. So you continue doing it, and you can get the whole correlator. But from this formula in particular, you can read off the OBE coefficients of, well, you can get the product, you can read off a product of the OBE coefficients of heavy with t squared and light with t squared. So this product is given by this, where A, B, and C are some formulas, some known formulas in particular. No, there are some, these are some formulas for A and B. So from here, you can read off the OBE coefficient of light operators with t squared. Turns out to be this. So in summary, from this exercise, you read off all the OBE coefficients of light operators with multi-stress tensors at leading twist. We didn't use holography by doing this, but you know, as I mentioned, you can use holography to compute some of these OBE coefficients. It's a harder exercise, so you will compute a few of them, and the two things happily agree whenever the holographic results are available. It's also useful to note that this heavy light correlator turns out to exponentiate in the sense that this function has a finite limit when you send delta light to be large. And remember, this delta light to be large limit is a limit which you can access from holography by computing a geodesic in the black hole background. And so that's a nice limit where you can compare things. So in particular, the bootstrap gives you this kind of expansion. So bootstrap, in fact, there is a closed form formula in this limit from the bootstrap. It has some, there's a closed form formula from holography. You can compare it with the bootstrap, and the two sides happily agree. Okay, so any questions about this? So the summary is that we can bootstrap plus ansatz completely fixes this heavy light correlator. Now let me talk about some combinatorics, connection with combinatorics. So to discuss this, let me go back to the two-dimensional case and remind you that in the two-dimensional case, the heavy light correlator, also known as Virasoro vacuum block, is known. And you can take a z goes to 0 limit of it, and it turns out that this function f, which appears in the exponential, it again exponentiates, and this function f, which appears in the exponential, behaves like a log, where a coefficient is a known function of mu. So it turns out to be this function of mu. This is work of these guys. And it's very easy to see that it's a solution of this quadratic equation. Very nice. So why is this quadratic equation important? Because, well, one reason why it's important, because the solution of it, B2, it turns out to be a generating function of the Catalan numbers. In other words, if you expand this B in powers of mu, the coefficients of the expansion are going to be the Catalan numbers. The Catalan numbers are just these numbers. And there are all sorts of ways to represent them. In particular, one way to represent them as the number of linear extensions of a partially ordered set. What is this? Well, a partially ordered set is a set of elements which are partially ordered in the sense that there are relations between some of these elements, which here are specified by these arrows. So this arrow means this guy is smaller than this guy, but it doesn't say anything about the relation between this and this. So in particular, each such partially ordered set admits linear extensions which correspond to various full orderings. So for example, how many full orderings does this poset have? Turns out to be 5 full orderings. And here's the example. So each of these tables have the same ordering as these arrows specify. Indeed, 1 is smaller than 4, 4 is smaller than 5, 1 is smaller than 2, 2 is smaller than 5, 5 is smaller than 6, and so on. So you can check that each of these guys has the same partial ordering as this one, but in addition, of course, each of them has full ordering, because 1 is smaller than 2, smaller than 3, and smaller than 4, smaller than 5, and smaller than 6. So there are five ways you can put ordering on this partially ordered set. And Catalan numbers turn out to be number of linear extensions of partially ordered sets with n boxes. So if I keep adding boxes here, I get higher and higher Catalan numbers. Incidentally, Catalan numbers also count the number of binary trees. Now, the equation for, so this is just B2, but it turns out that you can get the whole heavy, light correlator or Versor vacuum block from this Catalan number story. So what you do is you take this equation and you generalize it to a differential equation of this type. And the solution turns out to be precisely the Versor vacuum block. Interestingly, the solution satisfies this nice ansatz, which is the direct analog of the ansatz we had in 4 dimensions, but now it's in 2 dimensions. You can ask what happens with high spin algebras. And one thing you can do is you can consider heavy, light blocks of W3 algebra, where the spin 3 charge is large and its ratio with the central charge is finite. And again, we send central charge to be large. And then we assume the ansatz, exactly the same ansatz that, well, actually, we don't have to assume. What we observe, well, first of all, these blocks have been computed. There are like various ways to compute it, so they have been computed. And then if you start expanding them in mu, it turns out that they satisfy exactly the same ansatz as our 4-dimensional result satisfied. So that's interesting. And moreover, the corresponding coefficient in front of log z in the z goes to 0 limit satisfies a slight generalization of the Catalan equation, which is this. And in fact, you can write down a generalization of the differential equation to this 3-dimensional case. So if you write this equation, it turns out that the solution of it is precisely the heavy, light block for the W3 algebras. Okay, now how all of this is, so it's all very interesting, but it's still 2D. So how is it all related to 4D? It turns out that in 4D, in certain limit, again, as z goes to 0, the function that exponentiates behaves like log z with the coefficient, well, with the factor b of mu being a generating function for some for different number of linear extensions of partially ordered sets. So it's no longer Catalan. It's slightly different partially ordered set, but no, it's exactly the same way, the way it works. And the partially ordered set in question looks like this. So in 4 dimensions, the only difference from Catalan is you add a bunch of dots in the middle. So the numbers and then just as in the 2-dimensional story, in the 4-dimensional story, if I keep adding boxes here, I get higher and higher terms. And this way, I get the whole heavy, light correlator. So to summarize, the algebraic structure of the near light cone 4D correlator is very similar to that of 2D W3 correlator. And in addition, the numbers that appear in 4D are generalizations of Catalan numbers that appear in 2D. What we don't have at the moment is an equation for the generating function for these numbers. If we had it, then we would be able to write down the differential equation and solve this problem. And then we would have the full heavy light correlator solution for the case. That would be nice. Questions?
Hey, it's me again. So what happened to 3 dimensions?
Oh, well, we don't know.
Is it because of the you don't know the conformal block, or
Yeah,
is it harder? Okay,
that's the reason. But in principle, it should be a solvable problem. Definitely,
okay.
you know, for many of these things, you don't need to know conformal blocks. All you need to know is that the lightcone behavior of the conformal blocks. That, in principle, no, it should be solvable. So, but hasn't been solved yet.
I see. Thank you.
Okay, so if there are no more questions on this, let me go over to the second part of my talk, where I will discuss thermalization, thermal physics from all of this. So first of all, everything I've said so far was confined to leading twist sector. So all these T's were leading twist T's, but we can, in principle, do bootstrap for subleading twist, sub-subleading twist, and so on. However, well, so in holography, as I mentioned, the leading twist OP coefficients are not affected by the coefficients in front of high order derivative terms in the bulk. So there is some serious universality going on. Yet, if you add other terms in the bulk, which correspond to finite gap in the boundary CFT, then you can see that there are corrections to these OP coefficients. So there's no full universality. Don't expect that, let's say, you take n equals O super n mills, you consider finite lambda, not infinite lambda, but finite lambda, the OP coefficients that we've been discussing will be different. So there's no full universality. So but the natural question is there some universality still? So the answer turns out to be yes, and it's related to thermalization. So first of all, let me just mention that the contribution of some conformal family to heavy light correlator is given by this formula, where G is a conformal block, P is the product of the OP coefficients, and when we only consider leading terms in 101 expansion, we take the leading behavior of the heavy T to the K OP coefficient. So we're only interested in the term that scales like delta heavy over T to the K. Well, in this whole product, that's the leading term in this guy scales like this. But as you remember from the formulas for these OP coefficients, there are this is just a leading behavior, and there are extra terms. So what we're going to see is that this leading term is actually universal. It's related to thermalization. So how do we see this? Well, so correlator at finite temperature can also be written in, so you can also decompose a finite temperature correlator in terms of contributions of conformal families. And it's the same conformal blocks that appear in this correlator as the ones that appear in heavy light correlator. In other words, the kinematics is completely fixed. So as far as the kinematics is concerned, there is no difference between the light correlator in the heavy state and the light correlator in the thermal state. So that's what I just said. In fact, you can actually see it explicitly. So in certain examples, you can check that the conformal blocks at finite temperature are known. You can see explicitly how you get them from the heavy light conformal blocks. Now, then if we have thermalization, or at least here, let's discuss only the stress tensor sector. So thermalization is a statement that the one-point function of the multi-stress tensor in the heavy state is equal to the thermal one-point function of the same operator, where beta is determined by this equation. Beta is inverse temperature, delta heavy is the conformal dimension of the heavy state, and F is the free energy of the system. So thermalization happens if this is true, and then if this is true, then because the conformal blocks are the same, the 2-point functions will also be the same in the heavy state and in the thermal state. But is this true? Well, for the stress tensor, it's fairly easy to show that it is true, because for the stress tensor, this 3-point function is completely fixed by the word identity. So people showed that it's true. Now, on the other hand, large N factorization implies that the K stress tensor computed at finite temperature is the same as the T mu, the single stress tensor computed in the finite temperature to the power K. So this is large N factorization. And this is a statement that the T mu at finite temperature thermalizes. And this 3-point function is completely fixed by word identity and is proportional to delta heavy. So in other words, we get the following formula for the K stress tensor, that its expectation value at finite temperature must be equal to delta heavy over K, delta heavy to the K over Ct to the power K over 2, up to some number, which is theory independent. So therefore, thermalization, so the left-hand side, so thermalization is this statement. So the left-hand side is this, and the right-hand side, which is determined, is this, times some number, which is theory independent, plus some corrections, which are 1 over Ct. But this is the statement, so thermalization is equivalent to the statement about the leading behavior of the OPE coefficient of heavy operators with the multi-stress tensor. And this is something you can actually check. So not only you can check it in holography, but you can also take some other theory, like free theory, and observe that this is still true. So this alpha coefficient is going to be the same as in holography. So you can compute it in any theory, observe that this is true. So you conclude that the stress tensor, multi-stress tensor operators thermalize in all CFTs. Well, I'm sort of getting ahead of myself, really. So far, well, I mean, depends on like your level of optimism. So far, I just said that in some free theory and holography, you get the same result. So it's probably true for all theories because these things are so different. But you can have other arguments that that's the case. So in particular, you can have a bootstrap argument where you consider this diagram, and this diagram is proportional to OOT squared, lambda OOT squared. This is the OPE coefficient you're after. And in the cross channel, the main contribution comes from the same scale operator. This OPE coefficient is fixed, so you conclude precisely the same scaling. The coefficient, again, is going to be theory independent. So that would give you the same result. So the conclusion of this is in all large T theories, operators, multi-stress operators to thermalize. Now, let me, in the remaining 5 minutes, let me make some comments on heavy TT correlators. And I'll just mention a couple of puzzles that appear if you start thinking about heavy TT correlators. And I want to solve these puzzles for you. So this is going to be just an appetizer. So in the scalar case, so if I want to consider heavy TT correlator, I have 2 issues I have to deal with. One issue is that the conformal dimension of this guy is now integer. And there are issues when conformal dimensions of light operators are integers. Because if you remember the formulas, they had poles. The OPE coefficients of light operators had poles of the type 1 over delta L minus 4. And the physics of these poles was that there had to be a pole coming from the double trace operator, and these 2 poles would cancel, and this cancellation produces a log term, this type. So then you can ask a question, what's happening in this case? In the light case, you could not even compute the coefficient of this log. It was not something that you could compute, either by bootstrap or by holography. It was beyond our sort of power. So then the natural question is, are we going to be able to compute it for the TT case? So that's going to be hard. And the second question, another complication that appears has to do with large CT counting. So the leading behavior of the TT to T squared OP scales like 1. And then as a result, the contribution of double stress tensor to heavy TT correlator is a product of these two guys. So this guy scales like 1, and this guy scales like delta heavy over CT, which scales like CT to temperature to the 8th. Well, let's forget about the temperature. The point it scales like CT, while the connected contribution scales like order 1. So for light, we would have something order 1. So if you're computing something in holography, for example, you're computing something like TT correlating holography scales like 1, and not like CT, and well, in this normalization, and everything is unit normalized. So, and I'm talking about normalization where T, the expectation value of T is square root of CT. So this T is the canonical normalized T over square root of CT, in other words. So this means that you are interested in the connected contribution. You have to have access to one over CT corrections to the B data, and that includes anomalous dimensions of stress tensor, of the double stress tensor. So all of this is going to complicate your life, and so it's a fairly non-trivial question to ask: what's going to happen for the HHTT correlators? So let me summarize. Well, one thing we can do is we can compute heavy light correlators to all orders mu tilde, which is related to mu, using bootstrap. We observed that the form of this function exponential in b-dimensional CFT is exactly the same as the form of the corresponding function for W d over 2 plus 1 algebras in 2 dimensions. So particularly when d equals 4, it becomes a W3 algebra. And we can write equation for generating function in the Wn algebra case. Unfortunately, we cannot do it in high dimensions yet. We observed complete agreement between bootstrap and holography in a variety of settings. We observed that the stress tensor sector thermalizes. And some of the questions that are on the to-do list is whether we could find a nice form of heavy light correlator. Maybe that's related to finding the generating function for this number of linear extensions of these posetsets. A related question is whether there exists some symmetry behind near lightcone correlators that is responsible for all this amazing structure. And there have been a few papers on this. Still, I think it's a question that we don't know answer to. And finally, it would be nice to understand the thermal physics. So maybe all this technology will be useful for making progress in thermal physics. Thank you very much.
Thanks, Andrei. Very nice talk. We've had some questions, but let's have more. So I have to. So? I have hands. No, it's clapping. Yeah, some people were clapping. I mean, we also want questions. In the meantime, I see you mentioned so in the last part, is what do you mean by hydrodynamics here in this?
Oh, well, it's just it's just a statement that in principle, no, if you completely compute the two-point function of the stress tensor, a CFT, you can get all the hydrodynamic information from it. So that's basically what I mean by hydrodynamics.
I see. Any more questions? I see 15 people here. I'm sure somebody has a question. If not, I will still ask for questions about after I stop the recording to see if somebody was shy and don't want to be recorded. But okay, anyway, let's first thank Andrei again, and say we see next week for Rob Meyer's talk. So now let me stop the recording.